All right, let's get right into it. Today, we're embarking on a map reading expedition. But we aren't looking at continents or oceans or anything like that. We are venturing straight into the heart of the Earth. We are going to decode the literal blueprints of the ground we walk on by understanding something called a phase diagram. If you've ever looked up at a massive mountain and wondered how it actually came to be on a purely chemical level, well, you are in the exact right place.
Okay, let's dive into this by asking a really deceptively simple question. What exactly is magma? I mean, your mind probably jumps immediately to glowing red lava erupting from a volcano, right? Just some kind of uniform melted rock. But I want to challenge that basic understanding for a second. It's actually a lot more complex and, honestly, a lot more fascinating than just a river of melted stone.
To really get a handle on this, you kind of have to think like a chef. Picture magma as this massive, bubbling pot of hot soup, just loaded with all sorts of dissolved ingredients. And just like when you're simmering a complex reduction in the kitchen, as this magma soup starts to cool down, some incredible things happen. Different minerals literally come out of the liquid. They crystallize at completely different temperatures. And as those solid pieces drop out of the soup, the recipe of the liquid that's left behind, it keeps changing. It is a highly active, dynamic process.
And that brings us to the ultimate puzzle geologists have to solve. Imagine staring into this giant cooling pot of rock soup and asking yourself, okay, at this specific temperature, with this specific mix of ingredients, what actually exists right now? Is it all liquid? Is it solid rock? Or is it a mix of both? Well, a phase diagram is simply the map that answers that exact question. It gives us a crystal clear visual guide for this whole geological journey.
And this brilliantly illustrates what we actually mean when we talk about a phase. For these diagrams, we keep it strictly binary. We are just evaluating the state of our material. We're constantly tracking the balance between the liquid, molten magma and the solid crystals that are forming. So whenever we talk about a phase diagram in this explainer, just remember we're looking at a chart that tells us which of these phases, liquid or solid, gets to exist under certain conditions. So let's actually look at the coordinates of our map, starting with the simplest case, a binary system. Now, binary just means we're pretending our magma only has two ingredients, just to make it easy to track. On the x-axis along the bottom, we're tracking composition. This spans from component A over to component B, like, say, measuring how much silica is mixed with some other mineral. Then, on the y-axis up the side, we track the temperature, literally just how hot is this soup. By cross-referencing how hot it is with what it's made of, boom, we find our exact location on the map.
Let's move to the map itself and see how this builds. Because just like a geographical map has borders between countries, our magma map has two absolutely crucial boundary lines. And these lines separate entirely different states of existence. Now, what's really interesting about this slide is how absolute these two territories actually are. First up, we have the Liquidus line. If your temperature and composition put you anywhere above this line on the chart, it is simply too hot for any crystals to survive. Everything is 100% liquid. Then, down at the bottom, we've got the Solidus line. If the temperature drops below this boundary, the soup is completely frozen. Everything is solid rock, literally no liquid left whatsoever.
So we've got the totally liquid zone up top and the totally solid zone down below. But I bet you're wondering, what exactly happens between the lines? What on earth exists in the geological borderlands between the Liquidus and the Solidus?
Well, the answer is this chaotic, absolutely beautiful mix. Right between those lines, we have liquid and crystals just existing together. This middle zone is where all the action happens, really. This is where our hot magma soup is actively cooling down, and as it cools, it's constantly changing its chemical identity. It's essentially a hot, slushy mixture of molten rock and freshly formed minerals. Let's actually trace that journey step by step to see how this plays out in real time. We start at step 1, way up high above the Liquidus line. It's fully liquid, super hot. In step 2, the temperature drops, we hit that Liquidus line, and suddenly the very first crystals begin to form. Now step 3. As the cooling continues, more and more solid crystals show up. And remember our soup analogy? Because those new crystals are pulling very specific ingredients out of the mix, the composition of the liquid that's left behind totally changes. Finally, in step 4, we hit the Solidus line and the whole mass locks up into fully solid rock. This entire sequential process we just walked through, geologists called this fractional crystallization. But wait, there is a really fascinating twist on our map. If you follow these boundary lines down, you'll eventually hit a very special intersection called the Eutectic.
I want you to really focus on this. The eutectic is the absolute lowest temperature where a liquid phase can possibly exist on the entire diagram. When the cooling magma hits this exact, precise point, two different minerals crystallize together at the exact same time, and the remaining liquid just solidifies incredibly fast. It's basically the grand finale of the whole cooling process. Okay, let's zoom back out for a second. We're looking at all these microscopic chemical changes, the liquidus, the solidus, that wild eutectic point, but understanding this is how we decode the solid earth around us. The rocks you see when you're out on a hike, they aren't just random chunks of stone. They are the frozen, historical record of a magma soup's journey across one of these exact phase diagrams. So, the crucial point is, this is exactly why phase diagrams are the ultimate tool in igneous petrology. Scientists don't just stare at these charts for fun. This map tells them exactly which minerals are going to form first as a massive magma chamber cools under a volcano. It shows them how that magma evolves over time. It answers the fundamental question of why different igneous rocks have completely different chemical makeups, even if they started from the exact same underground source. It's the literal blueprint for how rocks are made. To bring it all together, you can basically think of a phase diagram as a master recipe chart for magma. It really is that straightforward. If you know the temperature and you know the composition, the chart guarantees you will know exactly what minerals are forming and exactly when they're going to show up. Which leaves us with this final, honestly incredible thought. Phase diagrams are the secret code of magma. They reveal how molten rock turns into the solid earth beneath your feet. And you know what? We've just deciphered a piece of that code together. The next time you pick up a piece of granite or some rough volcanic rock, just remember that you're holding a frozen moment in time, perfectly mapped out by the laws of temperature and composition. So the next time you're looking up at a majestic mountain range, ask yourself what ancient, secret recipe is frozen right there inside of it. Thanks for joining me on this explainer today, and keep questioning the incredible world right beneath your feet.